have any questions during the stream, feel free to ask them in the chat, and we're going to handle these questions during the stream. And if the questions will be really, really complex, then we can always have some time to handle it later via other medium. So welcome once again. It's an introduction to fairness in machine learning, powered by Fairlearn. And as PyLadies Amsterdam, I would like to introduce to you today Hilde Weerts. I do hope that I pronounce it correctly, right?
Close enough.
Close enough. Great to know. So what's important to say that Hilde is actually an artificial intelligence engineer at Eindhoven University of Technology, and she works in research, education, and of course tools for fair and explainable machine learning. And the last but not least, she's also maintainer of the Fairlearn project. And now I think it's time to give the floor to Hilde because she can definitely talk more about this wonderful library and also why this library was created.
Definitely. All
Okay,
right.
Hilde, time to share your screen.
All right. Let's see if this works.
We do hope.
Bam.
Okay, great.
Just a sec so I can.
Yes, so you can switch.
All right. Yes. Okay. So you cannot see me anymore, but I'm still here. I swear. All right. Yeah. So like Aljona told you, my name is Hilde Weerts. I'm an AI engineer at Eindhoven University of Technology, and today we're going to learn a little bit more about how we can measure fairness of machine learning models. Let's see if I can go to the next slide. Yes. Awesome. All right, so I'm going to start with a very short presentation about algorithmic fairness, and then I'm going to give you a short introduction to the tutorial that we're going to do that you can also find on the GitHub repository. All right. So as you may have already read in the description of this tutorial, we're going to talk about algorithmic fairness, and this is the definition of algorithmic fairness, so to speak, is the idea that algorithmic systems, so that's in the broad sense of the word of algorithmic systems, should behave or treat people without unjust or prejudicial treatment on the grounds of so-called sensitive characteristics. So sensitive characteristics could be more traditional characteristics such as gender, race, sexual orientation, stuff like that, but it could also really depend on the case at hand. And we've seen in the past few years quite a few incidents, if I can call them that, where we've seen how machine learning systems can actually become unfair in one way or the other. So first of all, we have this example of an AI recruiting tool that was being developed by Amazon. And what they found is that this tool, it scanned resumes, and then based on that, it predicted whether somebody should be hired or not. And it turned out that this model learned all kinds of things that were not associated with how good an employee would be, but whether they were a woman or not. So things like women's chess team were very important for the model. This tool was never used in practice, but it's an example of how things might go wrong. Another example that's very contemporary, I would say, in the Netherlands is in fraud detection. We've seen with the childcare benefits scandal in the Netherlands, we've seen that if algorithms are used in, unfair ways, they can really cause harm. And this is interesting because the childcare benefits scandal, the algorithm that was being used was actually super simple. So it wasn't like a very incredibly black box complex model, no, and still it could really cause quite a bit of harm. And then the final example that I have on this slide is translation. So surely you've seen this example before, but if we translate from languages such as Turkish in this example that are ungendered to a gendered language such as English, then you can see that we have that she is a cook, he is an engineer, can result in some stereotypical associations with particular occupations. So these are just some examples to show you what might go wrong. And actually, we can identify several different types of fairness-related harms. I've listed them on this slide. So the first that I want to talk about is allocation harm. So this is the type of harm where the system may extend or withhold particular opportunities, resources, or information to some groups more than to others. So an example here would be, for example, the jobs that we've talked about before in a hiring scenario. A second type of harm is quality of service harm. So this doesn't necessarily relate to allocation of items. It could, but it doesn't necessarily do so. But you could also have a system that simply doesn't work equally well for all groups. So, for example, if you have a skin cancer detection algorithm, but it only works on lighter skinned people, then that could be an indication of quality of service harm. The third type of harm is representation harm. So this could actually also be a cause of quality of service harm. So if some groups are underrepresented in the data, you can imagine that the quality of your model won't be equally good for those groups, especially if the data distribution differs a lot. But also, generally speaking, if a system overrepresents or underrepresents certain groups, that could also be already a type of harm. The fourth one is stereotyping. So this relates back to the translation example. Another example would be if you Google search an image search of CEO and all you get is white middle-aged men, then that could be a form of stereotyping harm. And this is particularly prevalent in unstructured data. So like videos, images, text, and stuff like that. Then denigration harm, and this is the case where the system is actively derogatory or offensive. So you can imagine a chatbot that starts spurring out racial slurs. There is also an example of Google Images that tagged a photo of two African American people as gorillas, which is obviously quite offensive. And the final type of harm that we can distinguish is procedural harm. And this is where a system makes decisions in a way that may violate social norms. So, for example, if we make decisions on who we should hire or not, maybe we feel like you shouldn't be penalized for being older, for example, in a particular model. So then, if the model would use age in a monotonic fashion, for example, you would violate that social norm. This is also closely related to interpretable machine learning. So today we're mostly going to talk about allocation harms and quality of service harm. And we're going to dive a little bit deeper into that during the tutorial, but this is just to give you an overview of all the different types of things that can exist. They can also occur at the same time. Actually, in fact, I think in many cases they will occur simultaneously. So yeah. And one question that you may have now is, how do these harms actually arise? So I always like to talk through this picture over here. So what you can see is when we are training a machine learning model, we're using training data, we're going to train a model, we have some model, and we use it to make predictions. And this is all in our very nice and abstract model world. So if you're a data scientist, then you are usually doing a lot of stuff here. But of course, the real impact of an algorithm happens in the real world. And this is also where you build your problem formulation, where you collect your data, and also where the actual impact of the decisions that you base on the predictions occurs. And in this process, we actually make a lot of small decisions that will impact what the final model would look like. And many of those decisions you make implicitly, and maybe they're based on practical constraints, such as the availability of a particular data set or something like that. And this is where those harms can arise. So basically, it happens when there is some sort of a mismatch between what we really care about, so our values, and how we have defined our problem, or how we are the decisions that we're making and what we're optimizing for. So for example, in your problem formulation, you can, if you are developing your requirements of your model, like, does this really reflect all the things that you care about, or maybe just the business value, even though you may have other moral values that are involved as well. Another question is whether the data is actually a good representation of reality. We'll also talk a bit more about that during the tutorial. What performance metric are you optimizing for? So this is kind of the translation from the things that we defined in our problem formulation to the machine learning context. Does the model actually make fair predictions? And perhaps even more importantly, does the system as a whole produce fair outcomes? Because usually, in many cases, the machine learning model is not the final thing that determines the decisions. Like it could serve as a decision support system, and then other people would make the final decision. So this is just a glimpse, and like I could talk about this for a long period of time, but this is just a very short introduction of all the ways in which things might go wrong. So just to conclude this very short introduction, first of all, we've seen that machine learning systems can reproduce, amplify, or introduce unfairness. We've seen different types of fairness-related harms, including allocation harm and quality of service harm. And finally, I've tried to explain how fairness-related harms can arise, mostly due to a mismatch between what we're optimizing for and what we actually value. So I hope this will become a bit clearer during the tutorial. But for now, if there are any questions at this point, then please post them in the chat.
I think people mostly thinking about their last days, what they done, and how they for what metrics they are optimized, and all the things, and they try to understand what kind of damage we could bring to the real world. So I think it could be the case, right?
Yes, everybody's reflecting right now.
Indeed, indeed.
Yeah. Well, let's continue to the tutorial introduction. So we're going to dive into a very specific case study, and it revolves around pre-trial risk assessment. And this data set that we're going to look into was collected in the United States. And that's also why I think it's good to give you a short introduction of the context of how this data was collected. So the goal of the tutorial will be to learn how to measure particular notions of fairness using Fairlearn. And we're going to look at the Compass recidivism prediction algorithm. If you have already seen something about algorithmic fairness before, then you're probably aware of this case study. So we're going to use this as a running example. And the learning objectives, because I am also an educator, so I like to define learning objectives, is to learn how to apply group fairness metrics in Python. We're going to look at some trade-offs between different group fairness metrics. And we're also going to look into how threats to construct validity, it doesn't matter if you do not know this word yet, you will at the end of the tutorial, and how it may impact downstream fairness-related harms. So about pre-trial risk assessment in the United States. So this is one step of the whole, I guess, criminal justice system that is currently in place in the United States. And what happens is that at some point, first, you need to get arrested. And then usually before you can go to trial, so this is basically where they decide whether you're guilty or not guilty, you will have to go through pre-trial risk assessment. And this is basically where the judges will assess to what extent releasing you might bring a risk to society, or it could be that they just want to make sure that you actually show up for your trial. So that's kind of the risk that we're assessing here. And then after the risk assessment, you have to await your trial, and then you actually go to trial. So this is all even before somebody actually goes to trial. So they're still just getting arrested and not already convicted or something like that. So this assessment is used to determine, like I said, whether somebody will be detained, and this is when they will go to jail while awaiting trial, or whether they will be released or not. And if they are getting released, then there's the question whether they will be released on bail or whether they won't be released on bail. And you will probably know this from the movies in the US, that bail is very often in monetary terms. So you actually have to pay money and then you could get released or not get released. If you cannot afford to pay bail, it is possible to get something called a bail bond, where you usually you kind of borrow the money, so to speak. But this is also at a fee of about 10% of the bill or something like that. That's non-refundable. So if you pay the bill, if I recall correctly, you will get it back if you actually show up at the trial. But if you don't, you have to pay it. But if you go for a bail bond, so if you couldn't afford the bill yourself, then you actually have to just pay a non-refundable amount of money to the person who will post the bill for you. So this is all very important to understand the context of what we're talking about here and what the consequences are of the model that we are going to assess. So in 2017 or 2016, I'm actually not 100% sure, there was this analysis of ProPublica, where they analyzed Compass, which is a recidivism prediction algorithm that is actually being used by judges in the United States. And they showed that this model failed very differently for African American defendants compared to white Americans. So we can see here, this is a nice little overview. So we have the percentage of false positives. You can see that it's like twice as much for African Americans and the other way around for the false negatives. And this is an incident that sparked a lot of discussion about fairness of machine learning systems, or of algorithms in general and machine learning systems in particular. And yeah, that's why I think it's a really nice case to dive deeper into in the tutorial. So without further ado, let's get to the Jupyter Notebook tutorial. All right. But let's see first if there are any questions right now. Feel free to post them in the chat.
Okay, we'll be checking.
I see no questions, but please do ask questions to the people watching.
Otherwise, I'm just going to assume that everything's crystal clear.
It is for me. It's going great. So.
Awesome. All right. So I tried to make this tutorial in a way that it's also. Ooh, why is this not closed? Quit. So you don't have to see all my WhatsApp messages. All right. So I tried to make this tutorial in a way that it's also readable without the introduction slides. So this means that we can actually skip this first part because this is what I just told you a few minutes ago. I think I'm just gonna make this one like this so we have a little bit more space. All right. Oh yeah, something that I didn't mention, and I think that's important to mention, is that if you have a false positive in this scenario, then it could have a big impact on the defendant's prospect. So I hope that I made that clear in this little figure that I showed you earlier, what the consequences actually are. Because if you are a false positive and you are going to be detained, you will have to await trial in jail. And this makes it much more difficult to prepare adequately for your trial. So that's important to know. And on the other extreme, we have false negatives, which could mean that dangerous individuals are released into society. And there's also a really nice tutorial created by, I don't remember exactly who created, but it was on Fact a few years ago, where they actually invited somebody who has gone through this entire process to give you a real good insight into the context. So if you're interested, I would definitely recommend you to go check it out. So it's also a final point that I want to make before we move on to the actual contents of the tutorial, is that that using algorithms for pre-trial risk assessment is not like uncontested, so to speak. So proponents, they argue that there is the option that it can lead to more efficient and less biased and consistent decisions compared to if you have as just human decision makers. But there have been quite some concerns about how the scores may replicate historical inequalities. And even if you could produce some sort of a fair risk assessment, then you could also still argue that that doesn't really solve the problem that we have with money bail. This is just to give you a little bit more context. All right. So the main definition of fairness that we're going to look into is group fairness. And this is a particular notion of fairness where we consider the extent to which particular groups of individuals are at risk of fairness-related harms. And those groups are referred to as sensitive groups in the rest of this tutorial. And like I explained earlier, they could be defined on legally protected sensitive characteristics, such as race and gender, but could also be very specific. So just an example, if you look at an automated essay grading tool, then perhaps the more traditional groups aren't as important, but it could be important to check whether the model works equally well for native speakers compared to non-native speakers of a language, for example. So we're going to look into three group fairness metrics called demographic parity, equalized odds, and equal calibration. And these are the three, I would like to say, main group fairness metrics that are used a lot in fairness literature. And we're going to dive deeper into what these words mean and when you should use a particular metric or not. So first we're going to import all the things that we're going to use. We're just going to use pandas, numpy, matplotlib. From Fairlearn, we're going to use quite a few different things, and also we're going to use a few functions from scikit-learn. So let's import those. Right. So we're going to use the data set that was actually collected by ProPublica, which I explained earlier is the organization that kind of revealed how Compass might be unfair. And they collected this data through public records request in Broward County in Florida. And we're going to use the pre-processing steps similar to the ones ProPublica used. I'm not going to dive very deep into those. But yeah. Let's see. Oh, not sure if this is actually necessary, but yeah. Okay. So what does the data set look like? So we have a few columns. So we have the sex of the defendant, which is measured as US Census sex categories. So this is just what they were able to retrieve. I do not know whether this is the sex that is on their passport or whether it's some other version of gender or sex, but this is what we have, the data that we have. Age. We also have the race of the defendant, and this is the race that was, as it was measured in Broward County's records. So this is an adapted version of the US Census racial categories, and it includes African American, Caucasian, Hispanic, which is more of an ethnicity, I think, than race, but it doesn't really matter, and Asian, Native, and Asian and Native American. We also have decile score, so that's this one over here, and this is the Compass score expressed in deciles of the raw risk score. Yeah, here's some more information about how these are collected. I'm not going to dive very deeply into this, but it's good to see that 1 to 4 is considered as low, 5 to 7 as medium, and 8 to 10 as high. Then we also have the priors count. This is the number of prior charges up to now, excluding the current offense. 2-year recid, so this is the 2-year recidivism, although I should probably say that it's the 2-year re-arrest. So this is whether the defendant has been rearrested within 2 years after the current charges were registered. And then we have this little column over here. So that's just generated here. And all we do here is just binarize the decile score based on what we've seen here. So everybody who's medium or high is considered as a true, and all the other ones are considered as false. All right. So now let's first have a little look at the distribution of the demographics in the data set. So we can see that males are quite overrepresented compared to females in the data set. And we can also see that African American and Caucasian people are also quite common in this data set, and Hispanic other quite a bit lower, and Asian and Native American very small subgroups. So in the remainder of this tutorial, we will kind of replicate some of the analysis that ProPublica did. So we're going to focus on African Americans and Caucasians. This will also make it a bit easier to show you all the different fairness metrics, but you could easily also consider more categories, and yeah, you will get just some additional insights. So we're just going to select those. So now our data set only contains people for which the race was African American or Caucasian. All right. So now we're going to get to our first fairness metric. So this is demographic parity. And demographic parity can be seen as a measure of allocation harm. So I've discussed allocation harm before, and this is a situation where the system disproportionately extends or withholds opportunities, resources, or information to some groups. And we can measure this as differences in the selection rate of the algorithm. So what this means is the proportion of positives equal across groups. And for example, in a hiring scenario, this could mean that that the proportion of applicants that are female, then the proportion of people that we actually hire based on what the algorithm said is the same in the group of women compared to the group of men, or compared to the group of any other gender that you prefer. Yeah, so what this means is that the output of the model is independent of sensitive group membership. And this is the formula. So here we have the predicted class, we have group membership, and we want that the probability that somebody is predicted to positive is equal for some group A and some other group A prime. So it's very good to realize that this metric does not depend at all on the ground truth data that we have. So as you can see, it only has y hat, which is the predicted target variable, but it doesn't contain any information about the target variable. So you could ask, like, when should we use demographic parity as a fairness metric then? Because it doesn't take into account our target variable. Well, this is actually on purpose, because the underlying assumption of this fairness metric is that either everybody is actually equal, even if we do not see it in the data. So for example, we may believe that the traits of whether you are suitable for a particular job is independent of your gender. But it could be the case that due to social biases in historical hiring decisions, that the hiring decisions do not adequately represent this. So that's why, so basically we're saying we believe that the target variable is not an adequate measure of what we actually want to measure. And the other scenario would be that maybe we do believe that it's a good representation of reality, but we want to make up for wrongdoing in the past. So for example, again, with the gender in job suitability, well, maybe there were some lacking opportunities for some groups compared to others, and we want to make up for those things. So these are typical scenarios where demographic parity would hold. Generally, I do think it's always good to just measure this to get an idea of the proportion of people that you're getting positive predictions for, especially if it's used to distribute resources like a job or loans and stuff like that. But it is good to realize that if you want to enforce demographic parity and the base rates in the data set are not the same, so the proportion of positives in the ground truth target variable are not the same between groups, then you will have to treat some groups different from other groups. So it could be that two people that have the exact same features, apart from race, they would get a very different prediction. But we will talk a bit more about that when we get to the limitations of some of these metrics. So yeah, so now let's get to actually computing these. So we can use Fairlearn's metric frame to analyze the fairness of the compass scores. So metric frame is a nice class that kind of, I think it's somewhere in between what you would expect from pandas and what you would expect from scikit-learn. So the API is also will be quite intuitive. So we have the following parameters. So first of all, we have the metrics. So this is some callable metric, and you can use any scikit-learn metric here. We also have some metrics that you can use in that are defined in Fairlearn. We have y-true, so these are the ground truth labels. Y-pred, these are the predicted labels, so the labels predicted by the algorithm. We have sensitive features, so this is a column of your data set that includes the sensitive features. We also support multiple sensitive features. And then we also have control features, and this is a very specific parameter that also contains a column of your data set. But this is features that you might want to investigate disparities for separately. So you want to sort of control for this particular feature. Oh, I just realized that you cannot actually see, but I did the, what you call them? The hack, yes, I did them by myself. So for example, you might expect that some particular feature could explain some of the observed disparities between sensitive groups. So for example, if you are predicting the amount of salary that somebody should get, then you could say, well, the number of hours that you work, we should control for that when we compute whether there are disparities between. So there's sort of like explainable features can be included here. So metric frame has a few things that you can look into. So we have by group, and this is a data frame with a metric value for each group. We have overall, this is just the metric value for the entire data set. And then we can also compute all kinds of methods to compute, for example, the absolute difference between groups for each metric. But I think it will become clearer when we get to actually doing this. So in addition to a metric frame, we also have some predefined fairness metrics, and I will showcase those as well. But under the hood, they all use metric frame. So that's why it's probably the easiest if I first start with that one. All right, then we can start with the first exercise where we're going to use metric frame to compute differences in selection rate, which is basically demographic parity. All right. So we have in Fairlearn, we have a metric, so like a base metric that is called selection rate, and all this does is compute the average over the target variable that you have predicted. So just the proportion of positives, basically. And then we have y-true. So in this case, like for selection rate, this doesn't really matter because the selection rate only looks at y-pred, but just for consistency, we have it here. So I could basically use anything here. So I'm just going to use the decile score cutoff, which, if you remember, is the binarized version of the compass score. And more importantly, we're also going to use this at y-pred. Cut off, right? And then for the sensitive feature, we're going to look into the race column. All right. Oh, invalid syntax. What did I do wrong? Oh, I forgot to close this one. Is it really a tutorial if you do not make any mistakes? I'm not sure. All right. So now we've computed this, but it doesn't really show you anything yet. So what we're going to do is we're going to look into by group. So this is what I explained before, a nice little data frame that will showcase the the computed metric for each group separately. And then we also going to print the overall score like this. All right. So here we can see that the selection rate of Compass is almost 0.6 for the African Americans, and for the Caucasians more around 0.3. So you can see that it's very different here. And this, as we will see later on, can be quite problematic. So what this means is that Compass predicts much more often for African Americans that they will get rearrested within 2 years than it does for Caucasians in the data set. So this is just a data frame, and if you have more metrics or if you use control groups and stuff like that, it will become bigger. And in some cases, it can be nice, especially if you are optimizing for something, to summarize it in one single number. And this is also what people would usually refer to as the actual fairness metric. I would definitely recommend you, though, to always first start with actually checking out the differences manually in the metric frame, because it can give you a lot more insight than just trying to squish everything down into one single number. But we can do that here. So we can use metric frame dot difference, and what this does, it computes the difference, and you can choose whether you want to compute the difference compared to the overall or between different groups. So here I'm going to go for between groups. And then we can see that the demographic parity difference, so the differences in selection rate is 0.25, which is what we would expect here. So we can also use demographic parity difference, which is a function that we have in Fairlearn. We can also use it directly to compute the difference in selection rate. And in that case, we can just repeat what we also put up here. So we have the data. I'm just using this one again, like the y true isn't really used here, but because for selection rate, we only consider y pred. Oh, I see, I forgot the D, right. Put in race, and then here you can see a method, and this is basically you define here whether you want, which is similar as you've seen here. So whether you will use between groups or overall. So this is the same thing. And then we can just compute it. Ooh, what did I do wrong? Oh, yeah, typos. Yes, there we go. So it's exactly the same as we've seen before, which is as it should be. So we have seen that the selection rate is quite a bit higher for African Americans. And you may wonder whether this is some disparity that is introduced by Compass by these scores, or whether we can see a similar pattern in the ground truth data, so to speak. And this, like the selection rate in the data, we can refer to as the base rate. So we can do the exact same thing here, but then rather than considering the decel scores cutoff, we're going to compute the selection rate for the actual recidivism prediction. So that's whether somebody will get rearrested or not. And here again, of course, we're going to put in race. And again, we can summarize this by computing the difference. And we can see here that the difference is, there is still a difference between African Americans and Caucasian in terms of selection rate, but it is much smaller compared to what is happening in the Compass scores. So there are many different reasons why this base rate difference exists even in the ground truth data. So apart from what is introduced maybe by the Compass scores. And one of these explanations, and I think this is very important to understand, is that the observed recidivism rate may not represent the actual recidivism rate. So like I've said a few times before, what we're considering here is rearrests. And that's just a subset of all cases of recidivism. For some people, we might not even see that they actually get rearrested, or because whether they will reoffend or not, just simply because they are not caught, so to speak. So it could be that these disparities are more reflective of racist policing practices rather than the actual crime rate. Another thing that could be the case is that there may have been some social deprivations that have caused the true underlying recidivism rate to be different across groups. So it might be the case that African Americans are indeed more likely to fall back into criminal behavior, but this might be due to circumstances that are out of their control, and also historical injustices. And of course, these two, like, they do not necessarily occur, like they could overlap, obviously. And there may also be other factors. But what I think is very important to realize is that you cannot know which two of these explanation holds from the data alone. You really need to understand how the data was collected, what the social context is of the model that you're building. Yeah, so that's just important to realize that we cannot learn everything just from the data. Sometimes the best thing is to just get away from your computer and talk to people to actually see what's going on. And something I've alluded to before already, and that is construct validity. So some of you might be familiar with this term. It's particularly useful, particularly often used in the social sciences. And what this means is, to what extent does the thing that we are, the measurement of what we're trying to measure actually measure what we are trying to measure, so the phenomenon that we are trying to measure. And this is a really nice way to think more deeply about whether your data is actually suitable for a particular purpose, especially in the context of fairness, because many of the fairness-related harms can be traced back to issues with construct validity. So just to give you a few examples, like in addition to that rearrests is not the same as recidivism, healthcare costs can be a biased measurement of healthcare needs. So it could be the case that the costs reflect patients' economic circumstances instead of their health. Historical hiring decisions are not necessarily equivalent to historical employee quality. Again, these could be caused by systemic or unconscious social biases in the hiring process. And similar to the rearrests, observed fraud is only a subsample of the actual fraud. And if you do not select the cases that you're going to investigate for fraud randomly, there could be some form of selection bias. And if this is associated with sensitive group membership, for example, because people have the fraud analyst may have subconscious biases here, then some groups may be over-scrutinized, and that can cause the observed fraud rate to be inflated compared to the actual fraud rate. And each of these cases of bias, for lack of a better word, is much easier to spot if we look at the data through the lens of construct validity. So we do have a nice little section introducing this concept in the user guide of Fairlearn. So if you're interested, I would definitely recommend you to check it out. But generally speaking, I think it's just a very important concept that as data scientists, we sometimes forget because we just get a data set and then we just take that as the ground truth. But it can be a very, very valuable process to first consider this idea of construct validity of the data that you have, whether you collect it yourself or not. So this was a nice little intermezzo. And now we can go to the second fairness metric, and this is equalized odds. So this is a measure of quality of service harm. So just to reiterate, quality of service harm is a scenario where the algorithm makes more mistakes for some groups than for others. Basically, you could use any predictive performance metric to measure quality of service harm, but something that is often used is equalized odds. And what we do here is that we see whether the false positive rate and the true positive rate or equivalently the false positive rate and the false negative rate, because the false negative rate is just 1 minus the true positive rate. And the idea is here that they should be equal across different groups. So just to give an example of quality of service harm, in a hiring scenario, we might mistakenly reject a strong candidate. So this is, again, under the assumption that or how do you say it, conditioned by the target variable. You can see that here. Like here, it does include y, whereas if we look back at demographic parity, we didn't have this conditions on the true ground truth variable. Yeah, so it could be the case that we mistakenly reject strong female candidates more often than strong male candidates. And this is this type of harm can particularly occur if the relationship between features and a target variable is different across groups. So the data distribution differs a lot between groups. And then if you have a lot more data for one group compared to another group, then this could definitely be a cause of quality of service harm. So an example that is often mentioned is a facial recognition system that doesn't work well for people with a darker skin compared to people with lighter skin. And this was mostly due because the training data set contained mostly lighter skinned faces. I would like to highlight, though, that it's not just a data problem, because as I've tried to show you in the slides before, it already starts earlier at the problem formulation and what you care about and measuring the things that you care about. Like if your team would have consisted of like a more diverse group of people, then probably you would have spotted these disparities in quality before deploying the actual model. But that's just my personal side note here. Yeah, so getting back to equalized odds. So it's simply the false positive rate and true positive rate should be equal across groups. So when should you use this? So as I already alluded at, the main difference with demographic parity is that we actually condition on the ground truth variable. And this directly implies that we believe that the target variable is a good representation of what we are actually interested in. Yeah, so that's what I wanted to say about that one. Yeah, and as we have seen in the introduction, if we have a false positive in pretrial risk assessment, can have very large confidence for the involved defendant. And actually, it has been shown that defendants might even just plead guilty just because they do not want to await trial in jail, because it could sometimes even be a year or more, and then it's easier to just plead guilty to a minor crime, even if you didn't do it. But that's more about the problems with the US criminal justice system rather than the fairness of the machine learning model. Okay, so now we're going to use metric frames similarly as before, but this time to look at equalized odds. So we can use multiple metrics in the metric frame. So you can just define them as a dictionary, and then we can just false positive rate, and then we have a false negative rate like this. So these are also included in Fairlearn, false positive rate and false negative rate. They're based just on scikit-learn metrics, but scikit-learn doesn't actually have these specific ones. They just compute the what do you call it? Confusion matrix. Okay. So here we can see the same numbers that we that I actually showed you earlier in the slide. So we can see that the number of the false positive rate is about twice as high for African Americans compared to Caucasians, and the other way around for the false negative rate. So this is exactly what ProPublica computed. And then we can use the metric frame difference again to compute the difference between groups. And as you can see, if we have two metrics, it will just, I can actually also just show you what this looks like. So this is just a series, a pandas series that gives you the false positive rate and false negative rate. I just wanted to print it. I don't know why I wanted to do that, but there you have it. We can also just, like before with the demographic parity difference function, we can also use equalized odds difference. Of course, these are two underlying base metrics. So we have to somehow aggregate that. And in this function, we have chosen to use the maximum of the false positive rate difference and the false negative rate difference. So if we compute that over here, you can see that it just takes this one because it was higher. So the false negative rate difference was higher. And it can be useful if you are, for example, doing some fairness mitigation, which we won't discuss in detail today, but in the next tutorial in February next year. Yeah, we're going to dive a little bit deeper into that. Let's see. Yeah, but again, I would always advise you to, if you are doing a real assessment of your model, always also look at this, because it gives you so much more information than just trying to squeeze everything into one single number. All right. Then we have another small intermezzo point that I wanted to make. And that is the problem of small sample sizes. So as you can see, many of these group fairness metrics, they rely in one way or another on calculating group statistics. And it could be the case that the number of individuals in the data that belongs to a particular subgroup is very, very small. So as we have seen in the beginning of the tutorial, the number of Asian and Native Americans in the COMPAS data set was very small. It was like 31 and 11 instances. And with those small sample sizes, your estimates of those group statistics, such as the selection rate, the false positive rate, etc., they become very uncertain. And then also your measurement of fairness becomes very uncertain. So basically, it will be impossible to accurately assess the risk of fairness-related harms, let alone mitigate them. And this is particularly important if we consider intersectional subgroups, like instead of just considering African American people and women separately, if you look at the subgroups such as Black women, then the groups become even smaller, and it can be quite problematic because actually fairness-related harms often accumulate at the intersection of marginalized groups. So this is just a small intermezzo to highlight the importance of making sure that you have enough data of each group, even if it's just for assessing fairness. And we can actually use the count function, which is in Fairlearn as well, to very easily compute the counts per group. We are working on adding some sort of confidence interval style things to the metric frame, but that's something that was under development, so it's not yet here. Yeah, and here you can see the same thing as we've seen before, and especially if you have like many different groups or you're doing your first estimates, then this can be quite a neat little trick to make sure that you take into account the count. Wow. Okay, so that's what I wanted to talk about, to tell you about equalized odds. So far we have seen demographic parity, which measured the differences in selection rates, which you can use if you believe that the thing that you're trying to predict might not be an adequate measurement of what you trying to predict. We have seen quality of service time metric, equalized odds. And there is also this third notion of fairness, and that is equal calibration. So North Point, which is the company that developed COMPAS, they actually responded to ProPublica's analysis that COMPAS scores are fair because their scores are equally calibrated across racial groups. Calibration, you're probably familiar with the term, but what this means is that the probability that you belong to a particular class is equal to the actual proportion of people that are classified as such, that they also belong to that class. So in the binary case, we can define it as such, where we're trying to look at the proportion of actual positives conditioned by the sensitive group membership and the predicted value. So, for example, if you have an instance that is predicted to belong to the negative class, then the probability that this instance actually belongs to the negative class is independent of sensitive group membership. And this boils down to equal, in the binary classification scenario, to the positive predictive value, so that's just precision, and a negative predictive value. So when should you use equal calibration as a fairness metric? So the underlying assumption of equal calibration is that every score should have the same meaning, regardless of sensitive group membership. So if you get a score of 0.7, that should mean the same thing whether you are in one sensitive group or in another sensitive group. So here the assumption again is that the target variable is a reasonable representation of what reality looks like, or what we want reality to look like. But it does not acknowledge that the relationship between the features and the target variable is different across groups. And in most cases, it doesn't really require you to do any active interventions, because we sort of get equal calibration for free. And without including explicit fairness constraints such as equalized odds and demographic parity, we often implicitly optimize for equal calibration. So I want to note that this particular notion of fairness does not very easily translate to the harms that we've discussed before, except maybe procedural harm, where some groups are treated like, if it doesn't hold, if 0.7 does not mean the same thing, then that could be a form of procedural harm. But it is quite difficult to see the direct harm that occurs because of that. And that's why I'm usually not a huge fan of equal calibration as a fairness metric, but because it is such a big part of this discussion about Compass, I think it is important to explain it to you here. Okay, so now let's go and look into that. So the positive predictive value, as I explained before, is equivalent to precision. So we can just use scikit-learn's precision score. The negative predictive value, we can just define a new function to compute that. It's basically the precision score, but then for the negative class. So all we do here is just use a different pass label, and then we get that one. So that's the negative predictive value score. And we can again use metric frame to compute this. So we can do precision score. And yeah, I'm just gonna copy paste that because I'm lazy like that. Oh, yeah. And because I make typos all the time, apparently. Is this how you spell that? Yes, it is. All right. So here we can see that the differences indeed look pretty small, and we can again compute it like this. So 0.05, 0.06, that's quite small. And at least compared to the other differences that we've seen. Yeah, so it does look like the claim of North Point that there is equal calibration that actually holds here. Another intermezzo thing that I really want you to think about in the future. So I've talked a bit about construct validity of the target variable so far, but something that is often forgotten is this idea of construct validity, but then of the sensitive characteristics. So in this data set, we have measured race as the specific categories, just the ones that were used by Broward County Sheriff's Office. But it's very unclear how these measurements were obtained. Like, is this some form of self-identification? Is this race category based on what's observed by police officers, or maybe something else? It is also unclear whether it was even possible to enter multiple categories for race, even though people might very easily identify with multiple races. And like, of course, in practice, we are usually already happy if we have some sort of measurement of these sensitive characteristics. But regardless, I would really advise you that if you have the opportunity to collect this data yourself, to really think through what you are actually measuring, because these are social constructs. And many of these are social constructs like race and gender. And there are many different ways in which you can actually measure race, and it could affect what you can conclude how you measure this. Just to give some examples, you could include self-reported racial identity, observed race based on appearance, observed race based on interactions. You could even have the racial identity that you think other people think you have. So that's like another dimension. So just many different ways in which you can measure it. And there are some differences in the conclusions that you can draw based on how you actually measured this. So that's just something that I wanted to note here. Like, for example, if your data is based on some sex category that only includes male and female, then what are non-binary people or people who identify as a different gender? Like, I mean, often sex and gender are, of course, conflated, but, or how do you say that? They are mixed as if they are the same thing, but it doesn't really matter. Just try to think a bit about how you define your sensitive characteristics. That's all I'm trying to say here. All right. Let's see how I'm doing time-wise.
You're doing good.
I think it's going well.
Yep.
Awesome. I see there's also no questions so far, but thank you, Marlene, for for noting that you think it's interesting. That means a lot. All right. So one thing that I didn't notice so far, didn't explain so far, we've mostly used the metrics that are already in Fairlearn. So equalized odds difference, demographic parity difference, those predefined functions. But we actually do have a specific function to make your own fairness metric based on any base metric, so to speak. And this is actually what we also use to derive those other predefined ones, but you can just use it for anything you like. So if you are in your use case, for example, maybe the false positive rate and false negative rate aren't as important, but maybe precision and recall are important, then you could make a recall derived metric where you look whether the recall is different between groups or not. So this function has a few parameters. So we have metric. So just that's the base metric, so to speak. We have transform. So this indicates whether we are considering the difference, the group min, the group max, or the ratio. We have sample param names. So this is a list of parameter names of the underlying metric, which should be treated as sample parameters. I'm not going to dive very deeply into this, but usually this will be, for example, the weight function. So if you have sample weight, then you could use that one. Over there, and let's see, what else do I want to note? Yeah, so it results in the same signature that we've seen before, but then with a sensitive features parameter and a methods argument. So under the hood, this function again uses metric frame to compute those metrics disaggregated per group. So we can make a custom fairness metric for let's see, for the NPV one that we've discussed before. So let me go back. I already selected it. Right. So this is just where we introduce the callable, and then let's just use the difference here. So now we have this function, and here you can see, I cannot see it like this, it doesn't really matter. But we can use this function now to compute the difference between groups, similar to before. So here you have you can input the, let's just do this in the right way. So we have y true, and we have y pred. So that's similar to what the negative predictive value score had as input. But now we can also input the sensitive features, and then we can choose whether we want to compute this compared to the overall or compared to between groups. also similar as before, like this. And then we see this is the exact same thing as we've seen before over here. So that's just a neat little function that I wanted to show you. Then finally, we can also further investigate the calibration. So we were looking at equal calibration if you lost track of what we were looking into. And we can also just compute, we can also plot the calibration curves just to see whether this is the case or not. So you may remember that we have binarized the compass scores, so the original D-style scores, but we can actually create a nice little calibration curve of the of each racial group. So if you have perfect calibration, you would have something that goes on the dotted line that's plotted here. So you can see that it's actually not very well calibrated, but the calibration does seem very similar for the two different groups. So that does seem to support North Point's claim that the scores have equal calibration. So at this point, we're going to get a little theoretical, but I do think it's important to note. You may think, well, all of these fairness metrics seem to have some value to them, right? So like there's some intuitions that sort of make sense. So why don't we just optimize for all of them at the same time? Well, the thing is that in most cases, that's not really possible, unfortunately. So we have seen in this tutorial that some understanding of fairness, so in this case, equal calibration, that does hold for compass scores, but both equalized odds and demographic parity are definitely violated. And it's good to realize that these findings are not specific to this case. And it has been proven mathematically that in cases where sensitive group membership is not independent of the target variable, so basically if the base rates are different between groups, and you want the output of the classifier itself to be well calibrated. So basically you want it to be as close to this as possible. So not necessarily per group, but just the overall classifier. Under those conditions, it's actually impossible for these fairness metrics to hold at the same time. And I'll try to explain that a bit more because it's actually quite intuitive. So if you consider, for example, demographic parity and equal calibration, then you can imagine that if group membership is related to the target variable, this implies directly that one group has a higher base rate, so proportion of positives, compared to the other group. So then if you want to enforce demographic parity, this means that you need to select more positives in the disadvantaged group than what was suggested by what you have observed in the target variable, right? Because you want to increase the selection rate compared to the base rate that is actually in the data set. So the positive predictive value, it must be different for each group because the proportion of the true positives that we predicted to be positive, it will be lower in the disadvantaged group. And we can make similar arguments for demographic parity and equalized odds, and also for equal calibration and equalized odds. I think demographic parity and equalized odds is probably the easiest to understand. So here again, if you have unequal base rates, that means that you have to classify some instances in the disadvantaged group, so the one that has a lower base rate, as positives, even if they should have been negatives according to the observed target variable. So if you want the scores to be well calibrated, so if you want the 0.7 to mean the same thing for each group, then you simply cannot satisfy both demographic parity and equalized odds because you will make some mistakes in quotation marks for the disadvantaged group. So again, this is why we only use demographic parity if we believe that the target variable may not be a super accurate measurement of what we're interested in. And of course, I'm not saying that you should always only compute demographic parity or only compute equalized odds, because both of these can give you very valuable information. But once you start to optimize for particular things, then you just really need to be very careful to consider what the assumptions are of the things that you are trying to compute here. And this is also what I'm trying to say in this this bold part, that like it has been these impossibilities and the impossibility of fairness and blah blah blah. It often has been presented as, oh, it's like the math doesn't hold up, but actually the dispute is more of the underlying understanding of what is fairness in our scenario. What do we consider fair? That's what you need to think about more, and not necessarily about the math, in my personal view. All right. Yeah. So so one thing that I think is very important is to make sure that any assumptions that you have about this, you just have to make it very explicit when you discuss fairness with other stakeholders, like people involved with the business or users of your system. All right, I'm gonna start finishing up the tutorial part. So there's a few practical challenges that if you want to start applying this in your daily work. So one thing that's very important is to identify the right sensitive, well, right, I mean, in quotation marks again, is to identify the sensitive groups. So you need to identify what groups of people might be at risk. And as I said before, how you're actually going to measure that. And it can be very difficult and very tricky. Like in this tutorial, we already decided, oh, it's going to be race, and we're going to look into that one. But of course, in practice, you need to find those groups yourselves, and you need to really have a really deep understanding of the context of where you're going to use your machine learning model. So especially if you're going to make predictions about people, always try to identify groups that may be at harm. But even in cases where you're not directly making predictions about people, this can be a problem. And it's something that the data itself cannot solve. You need to talk to people. Sorry to break it to you. Then there is the access to sensitive features. So there might be a privacy regulation or just practical constraints why sensitive features may not be available, and that makes it quite difficult to compute these group fairness metrics. Although I think that in the AI Act, they're trying to, like, that's a new regulation proposal that they're considering in the European Union, where they are thinking about making it legal in more cases to collect this sensitive information for the sake of analyzing fairness. But that's in the future, maybe something that would be nice. As I explained, small sample sizes can be quite problematic in a practical sense. So there's also just a few inherent limitations of these group fairness metrics. So first of all, we're computing averages across groups, but that means that we ignore within group differences. And it could be the case that there are actually subgroups that are at an even greater risk of harm, and then that can be disguised. For example, if we only look at race, but the actual harm occurs at the intersection between race and gender, for example, black males, for example, then that could be a problem. It's also just observational, so it doesn't consider at all like how the prediction was achieved. We only look at the outcomes, so that might also not give a complete picture of what you're interested in. It also doesn't include at all the individual experience. So we're assuming that a positive is just as positive for person A as it is for person B, even though that might not be the case at all. And then it's also very important to consider, and this is going back to that picture that I showed you it's already over an hour ago, so I don't expect you to recall it exactly. But there was this picture with a cloud, with the model and with the real world. And these fairness metrics only consider the direct output of your machine learning model, but not the outcome of your system as a whole, right? So, for example, in Compass specifically, the outcome is not determined by the Compass model directly. It is determined by the judges and how they interpret the provided risk scores. So, for example, even if we could somehow make the risk scores in such a way that that they are fair to some extent, if the judges with their own biases, interpret a risk score for one group differently compared to another group, then this could still introduce some bias and unfairness in the final result of the system. So trying to move beyond the mere algorithmic frame is always a good idea. All right, then we are at the main takeaways of the tutorial. So I hope that after this talk, you've learned how different fairness metrics actually represent different theoretical understandings of what fairness even means, and that is also reflected in the incompatibility of these fairness metrics. I also hope that if you take away one word, it's construct validity, because it's central in assessing fairness, in how you define your target variable, in how you measure sensitive group membership, and actually also in how you choose a fairness metric, because you can also apply construct validity to the idea of fairness, like, we are using equalized odds for measuring fairness, but what do we actually mean with fairness? And does this actually measure the thing that we are interested in? So it's also a useful tool there. Yeah, I've added some things that you can just, some discussion points that you can just think about. We don't necessarily have to, I don't expect you to give the answer in the chat, but I think it might be interesting for you. So, for example, you can think about what notion of fairness you think is most appropriate in this particular scenario, or maybe even more importantly, in scenarios that you are working on in your daily work. Another question, there is a way to account for unequal selection rates by using a different cutoff score for each group. So, for example, for one group, you would say, everything above 0.5 is a positive, and for the other group, you would say everything above 0.8 is a positive, which means that two people with the same score may be classified differently. And yeah, one nice thing to think about is, like, when do you think that that's fair, or if you think that's fair at all. And then finally, and this is a question that we get a lot at Fairlearn, it's like, so what value should my fairness metric have for it to be fair? And unfortunately, the very unsatisfying answer to that question is always, it depends. And in some cases, especially when you optimize for demographic parity, there will be some, how do you say that? Performance decline. There will be a decline in performance if you want to optimize for demographic parity. So how equal do you think is equal enough? That's also something you can definitely think about. So if you want to learn more about fairness, there is a nice book by Solon Moritz and Arvind, which is currently still in development, but they have quite a few nice chapters for you to look into. I also wrote some lecture notes for my bachelor's course at Eindhoven University of Technology on responsible data science. So you can also check that one out if you like. And also throughout the whole tutorial, I've sprinkled in some nice links to research papers or articles that can also be interesting for you if you want to learn more. So I think that's it for the tutorial. I hope that you've enjoyed it. So if there are still any questions, then feel free to ask them. I will stop sharing the screen now, and then you can see my face again.
Cool. Thank you so much. It's really, really valuable information. It was really good and outleg. Oh, I'm mixing that. No, I'm not mixing the words. Sorry, explanation. While waiting for some questions in the chat, if there will be some of them. Otherwise, probably people start thinking about all this whys, especially related to their everyday job.
Yeah.
I have a little bit question outside of the scope of this lecture, but a little bit about Fairlearn.
Mm-hmm.
So what you could advise to people who want to start with, for example, their first open source commits to Fairlearn library.
Yeah.
And this, and second, what kind of help is really needed right now for Fairlearn library?
Oh, yes. Oh, definitely. Yes. We actually are open to like many different types of contributions. So if you're really into coding, we have things. If you're more about, I know, thinking about practical considerations, like how should people do with this, if you want to dive into a particular topic. So we have a whole different range of things that you can do. So the easiest way to find out about these is just to go to our repository. We have a list of existing issues, which also have tags like, what's it say again? You have easy, the tag, and also like something like beginner or
The first issue, probably.
Yeah, something like that. Like it's a very clear tag. I just cannot come up with the term.
Yeah,
It's terrible.
like good first issue, something like
Yes,
that.
that's the one.
Something like
Wow.
that.
Yeah, the good first issue. Yeah, so we have those tagged, and it ranges a lot from adding additional documentation to adding new components to the library. But we also are very actively developing learning resources because we believe that you cannot really solve fairness just with technology. So you also need to step outside of your technology box. And we kind of try to lure people in with the tech, and then we keep them with the socio-technical context analysis. So that's the idea. But there's a lot of things that still need to be done. So if people are interested, we also have a weekly community call on Thursdays at 5 p.m. So it's like 1700. Every Thursday, we have a Discord, but you can find everything on the website fairlearn.org. But that's just some info. Oh, let's see. I see there's a question from Marlene in the chat. When studying data science, AI, is fairness something that's reflected in the curriculum? So currently, ethics is definitely reflected in the master's program. There's a specific course, though it's more philosophical oriented rather than very practical, so to speak. But in the bachelor program at the TUE, we have this course. Well, I teach the course Responsible Data Science, which is more of a more practical approach towards responsible AI. Because I feel that if you, and it's an elective actually, so people can just choose it. But last year we had like 100 students who were following the course, so that's quite a nice number of people. Because I personally, I really believe that if you teach ethics, it's important to also teach ethics from the philosophical point of view. Obviously, like it's very important, but it kind of detaches like this is Kant and this is deontology and this is utilitarianism. Like it kind of detaches it from what you're actually doing in your daily practice. So this is why I always really like to do a little bit more of this practical oriented work as well, because like if you are making a very small decision of like how we're going to measure fairness, like it's not necessarily a very small decision, like it doesn't really help you to have this big ethical framework in your mind, right? So that's
yeah, you have to apply it somehow.
Yes, exactly. And by doing this, I hope to be a little bit more of a bridge that's a little bit more practical, so people can do both and don't harm the world. No big goals.
We could start with small steps, right?
Yes, exactly.
I have a question. May I? Or
Sure, go on.
because it seems like wow, so. Do you know probably like what was the algorithm behind Compass, right?
Yeah, that's a fun one. So the algorithm that is behind Compass is proprietary. So so you cannot actually look at the algorithm itself. It's supposedly based on like over 100 features, which are based on like I don't know, like some questionnaire that people had to fill out. But there was actually a paper by Cynthia Rudin who figured out that if you create a model that only has two features, age and prior things, then it works just as well as Compass.
Oh wow.
And then you can actually consider like, do we think it's okay to use age and to use prior offenses as things in the model rather than some proprietary BS algorithm? But
Yeah.
what?
I would think they
This is
would after all this how do you say scandal, then they would force them to publish it. I mean, they do it with Google, with Facebook, so I would definitely do it with these people. Like ask them, what did you do? And basically, I mean,
yeah. I mean, surely they had the. I mean, I don't believe that they did like purposefully
no,
try
no,
to build something like
no,
this, right?
no, but just blindly,
Definitely not.
not just blindly, right?
Yeah.
They liked a bit blind.
And I
Thanks.
mean, in 2016, everybody was still blind to this problem, right? So we cannot expect people to.
Well, some things, I
Yeah,
mean,
yeah,
bias,
yeah.
error, come
I
on.
mean, so in this tutorial, we only discussed the fairness part, but that's of course just a very very tiny part of everything. Like if you look at the uh, childcare benefit scandal, for example, in the Netherlands, what you saw is that like this algorithm was super easy. Like it was super like it could have been very transparent and easy to explain to people, but it just used features that shouldn't have been used, and that resulted in over scrutinizing some groups. And then what actually went wrong was all the other things. Like, oh, it's a great example for my lectures. So accountability went wrong, transparency went wrong, like every it was just, yeah, everything on
So
top of
much
each other,
things.
which is all related not so much to this specific technical details of this algorithm, but how people used it, how people defended it, the culture of how it was used. Like it's
Yeah. So it's a
yeah,
really good real life example,
yeah,
right? Of like how it can become like a weapon.
yeah, yes, exactly, yeah.
I think we can have even more. Like there was like latest scandal with Zillow, that like it's the predictions of the price of the houses.
Oh yeah,
This, and it's actually I think everything boils down to the process. Who wants to be a responsibility for the output and how this
yeah,
output is used?
yeah.
So I think it's mostly this. I just remember like one of the use cases from our bootcamp that we did in the summer, and it was just like predicting amount of based on the solar and based on the sun and wind, predicting amount of alternative energy that could be produced. And then somebody just asked, "Oh, come on, what kind of like fairness questions could be attached to it?" It's like there is nothing. You just have like households that's like just use energy, and then just you want to predict how much energy could be generated, so people, if they want to cut off from the electrical grids, they know how to balance like their usage of the energy. But there is so much just for this like simple scenario, but there is so
Yeah,
much to add there. Imagine that there is like literally disparity between different regions. So
yeah,
you have region with more, let's say, poor people, or region with more, let's say, people with more income. They how much energy they use, like amount of square meters for. It's like there are so much to add to it, and although if you do something and generate predictions right now, it's immediately alterates the
yeah,
reality because
yeah,
people
exactly.
act
Yeah,
on it
very
and they
important.
change their behavior. So
Yeah.
I think it's so much things to it that probably we could just visit your lectures if it's possible.
Yes, please.
I'm not sure if it's if I'm not sure if I can invite people to the actual lectures, but if you are happen to be, if I can give them in person and you happen to be in Eindhoven, you're always welcome to join.
Great.
Deal.
Yes, we're going to think about it. But by the way, we still have the chance to be one of your wonderful tutorials, because
Yes.
little teaser. So first of all, thanks a lot for this beautiful introduction to fairness. For those who are really, really curious and interested to go much more in depth on these questions, not just technically, but as well, let's say, in everything that's around the technical parts. Oh, the doggy is here. Hello, doggy. Usually the dog is also interested in fairness. So we're gonna do deep dive with Hilde.
Unless it's for cats, right?
Probably get somewhere in the vicinity, right? Somewhere in
Yeah,
around.
she's on the other side.
Yeah.
I'm being a bit unfair.
So next year, you have an opportunity to see Hilde again, and we're gonna do deep dive into this matter. Our next event eventually will happen in December. It will be also really nice. I assume that we got biased, with like talking to really smart people, and because the next tutorial will be given by TU Delft professor, so I see we're going into the academia world. So we try to balance the sample. So for those who are interested how to communicate about the foundings and how the model works and everything around your machine learning models, so please feel welcome. We wanted to have this event at TU Delft, on-prem of the TU Delft. Unfortunately, due to the strict restriction, we decided to made it online, so it will be online December. And for those who first time watching us, just a quick recap. So we are PyLadies Amsterdam. We are a non-profit chapter. We are part of Global PyLadies, and our chapter specifically focuses on workshops and tutorials on different levels. And we do this to make sure that every Pythonista, despite the gender and any other biases that you could think of, has an access to specific materials. So I think that's conclude our session, right? Anything to add, Nancy, from your side, or Hilde?
I just wanted to thank everyone who's been watching so far, and I hope that you enjoyed it. And if you have any questions, you can always reach me on the socials. So
great. I think then we could finalize our session.
All right. Good night, everybody.
Bye.
Thank you for attending.